Let M be a finite monoid. An element A belongs to M is right invertible, then show that A is invertible. This video is continuation of one of my previous videos, Key Concepts to Understand Groups, Part 1, where I discussed the notion of binary operations, commutative and associative properties of binary operations. As a consequence, structures like groupoids and semigroups are defined. Link of that video can be found in the I button. Today, we will extend our discussion with the notion of identity element. Here it comes. An element E in a groupoid G composition is said to be a right identity if A composition E equals to A for all A in G. So here basically this element E is being applied on the right of every element. So when A compose E equals A for all A in G, we call E to be a right identity. So let's have some examples. So note that A minus 0 equals A for all integers A. And therefore 0 is a right identity in the groupoid Z with subtraction. Again, we can always construct new binary operation on any set to have this right identity element. For example, we can construct this, define this star binary operation on Z by this formula A star B equals AB minus A, which actually A times B minus 1, and we can see that when B minus 1 is 1, that is B equals 2, that is A star 2 equals A for all A in Z, and therefore 2 is a right identity in Z star. Okay, so similarly, analogously, we can define the notion of left identity. Now here it comes. An element A in a groupoid G composition is said to be a left identity if E compose A equals A for all A in G. So here you may note that E is being applied to left of every element to get back that original element. Now we'll have some examples. Already we have examples of right identity. Let's make use of this example. So we define star on Z by A star B equals B minus A. We just switch the position of A and B. So usual when we take subtraction, we take A minus B. So now we just switch the position of A and B so that when we think about 0 star B, then it is B minus 0, that is B for all B in Z, and therefore 0 becomes a left identity of Z star. Okay, and one can always define binary operations suitably so as to find some left and right identity. For example, we can define star on Z by this formula A star B equals AB plus 2B, and after A plus, this becomes A plus 2 times B. That means if you want this is always equal to B, that means you have to put A equals to minus 1, and we can see that minus 1 star B equals B for all B in Z, and therefore minus 1 is a left identity in Z star. So that's what we mean by left and right identity element. Now we'll see the notion of identity element. Here it comes. An element E in a groupoid G composition is said to be an identity element if E is simultaneously a left and a right identity element in G. That is, A composition E equals E composition A equals A for all A in G hold. Okay, so let's have some examples. Clearly, 0 is an identity element in Z plus, because if we add any integer with 0 in any order, then we will get back that element, and therefore 0 is an identity element. Similarly, 0 is an identity element for this groupoid n0 comma plus, where n0 is a set of non-negative integers, that is n union 0. Likewise, this identity matrix of order n by n is identity element in the groupoid set of all n by n matrices with integer entries with respect to the multiplication operation. Because if we multiply identity matrix pre or post, we will get back that matrix, right? Well, now we'll see if this identity element exists in a groupoid, then it exists uniquely. Okay, and therefore we will be calling this identity element to be the identity element. Let's see this. Now we see if identity element exists in a groupoid, then it is unique. To see this, let E and F are two identity elements in a groupoid G composition. Then by the property of E, A composition E equals E composition A equals A holds for all A in G. Let's give it equation number 1, and by the property of F we'll have A compose F equals F compose A equals A for all A in G. Let's give it equation 2. Now since 1 holds for all A in G, in particular one may take A equals to F. Then what we have, if we take A equals to F here, then we'll have F compose E equals F. F compose E equals F. Now similarly, equation 2 also holds for all A in G. So in particular one may take A equals to E. So that we'll have F compose E equals E. That is F compose E equals E. So the value of F compose E from one equation it is F, and from the other equation it is E. So they must be equal. That is E equals F, and hence the result follows. Okay. Alright. And therefore now onwards when we say identity, we will say the identity, because if it exists then it exists uniquely. Another thing, why we denote identity element by this alphabet E? Because of this German word Einheit. It starts with this alphabet E, and Einheit means unity in German. And that's the reason why we denote identity element in a groupoid by this symbol E. Now we'll see an elementary and an interesting fact related to left and right identity in a groupoid. So if a groupoid contains a left identity as well as a right identity, then they are equal, and that equal element is the identity element of the groupoid. To see this, let E and F respectively be left and right identity of a groupoid G composition, which means E is a left identity, therefore E compose A equals A for all A in G, and A compose F equals A because F is the right identity for all A in G. Now if we take A equals to F in this equation, then we will find E compose F equals F. And if we take A equals to E in this equation, then we will find E compose F equals E. So E compose F is F and also E, therefore E and F are equal, and hence E is the identity element in this groupoid. Okay, now we'll see the notion of monoid. A semi-group G composition is said to be a monoid if G contains the identity element. For example, N naught under addition. Yes, of course, one can check that it is a semi-group first of all, because addition operation is associative over here, and also obviously first of all plus is binary operation on N naught, and then this is associative, and 0 is actually the identity element here, and therefore it is a monoid. Then Z plus, one can easily check that trivially Z plus and Q plus are also monoids. And why Z dot is a monoid? Because multiplication operation is of course associative, and 1 is the multiplicative inverse, I mean that identity element under with respect to this binary operation multiplication. Similar thing happens for N dot as well, and therefore these are all examples of monoids. Moreover, you can see that set of all odd integers under multiplication is also a monoid. First of all, it is a binary operation because if we multiply two odd integers, again we will get an odd one, and therefore it is a binary operation. And since multiplication operation is associative in Z, so it is associative in any subset of Z, and therefore it is a semi-group. And obviously 1, which is odd number, which is an odd number, and therefore odd integer, and therefore 1 times anything is this, so therefore 1 is a multiplicative identity here, I mean identity with respect to multiplication here. So it is a monoid, but 2Z dot not, because it is a semi-group, because it is binary operation is satisfying, and then also associativity is there, but the identity element is missing here. Okay, so under multiplication 1 is supposed to be the multiplicative identity or identity element, but 1 is not an even number, and therefore it is a semi-group that is not a monoid. More generally, we can have monoids of this form for any set A to the power A, which means set of all maps from this A to this A. I mean the symbol is that B to the power A is denoted by set of all functions from A to B. Okay, so A to the power A is set of all functions from A to A, right? Is a monoid with respect to the composition of functions. Well, one can easily check that composition of function is associative by the defining property of composition of functions. And of course, the identity function from A to A is playing the role of the identity element in this groupoid. And therefore, this is a monoid. Okay. Now we can define discuss the notion of invertibility of an element. Let G be a groupoid containing the identity element E. Then an element A in G is said to be left invertible if there exists another element B in G such that B compose A equals E. So B is being applied from left side of A. And then this B is called a left inverse of A. Similarly, an element A in G is said to be right invertible if there exists B in G such that A compose B is identity. Here B is on the right of A. And similarly, B is said to be a right inverse of A. So now we will construct a monoid. Now we will see an element in a monoid might have a left inverse but not having a right inverse, having a left inverse but not having a right inverse, and vice versa, having a right inverse not having left inverse. So to find such element, let us consider this monoid n power n, that is set of all functions from natural number to natural numbers, set of all maps from n to n. Okay. All right. So first we want to construct a function f from n to n having only right inverse, which means we want to construct f in such a way that f composition G is identity on n, because this is the identity function, is the identity element for this monoid, and of course the composition is the composition of function. And so basically we want to construct a function f such that f is surjective but f is not injective. All right. So with this in our mind, so let's try to find this f. So this is natural number set, and let's say this is natural number set, and elements are 1, 2, 3, dot dot dot, and here as well. So 1, 2, 3, 4, 5. Okay, now we want to define a function which is surjective but not injective. All right. So what we can do, we can map 1 to 1, and then 2 goes to 1, 3 goes to 2, 4 goes to 3, 5 goes to 4, so on and so forth. Okay. So the rule is that, so we define f. So we define f from positive integers to positive integers by f of 1 equals to 1 and f of n equals n minus 1 for all n greater equals 2. All right, then certainly f is surjective and it is not injective. So let's try to figure out the function g. So how can we construct g? So now we define so we can take 1 definitely has to go to 2, 2 definitely has to go to 3, so on and so forth. So we can define g by the right shift, that is gn by the element 1, n plus 1 for all n. Then what is this composition? F compose G. So note that F composition G of n. So for n equals to 1, okay, so G of n is n plus 1. So F of n plus 1 and since n is a natural number, n is greater or equals to 1, that means n plus 1 is greater or equals to 2. So this rule will apply, and that is n plus 1 minus 1, that is n. So this holds for all n belongs to n, which means the composition f compose g is actually identity function on n, or identity element in the monoid n to the power n. So this is this. So therefore we can say that f is the left inverse of g, or g is the right inverse of f. And note that this element f cannot have a left inverse, because if f has a left inverse, which amounts to say that there is another function h such that h composition f is identity. And since identity function is injective, so is this f. But here this function by the construction f is not injective, because these two different element 1 and 2 both maps to the point 1. So this is the rule of f. So it is certainly not injective, so h doesn't exist. That means f only has the right inverse, but f does not have its left inverse. Likewise, g has the left inverse, namely f is the left inverse of g, but g cannot have its right inverse. So what happens if g has a right inverse, which amounts to say there is another function g composition h is identity. Now which means since identity function is surjective, g is surjective. But here if you look at the construction, g of n equals to n plus 1, that means the point 1 does not have any preimage. So g is not surjective. So such a function h can't exist. So that means f does not have its left inverse, and g does not have its right inverse. So one can construct elements having only one type of inverse in this way. All right, now we'll go to our next concept of next notion, I mean the notion of invertibility of an element. Let's see this now. So let G composition be a groupoid containing the identity element E. Then an element A in G is said to be invertible if there exists an element B in G such that B is simultaneously a left inverse of A and a right inverse of A, which amounts to say that A compose B equals B compose A equals E. And then this B is said to be an inverse of A. So let's have some example. Clearly minus A is an inverse of A in Z plus, because if we add minus A and A, we will get the identity element. So this criteria is fulfilling, and of course that addition operation is commutative. And this 1 and minus 1 are the only invertible elements in this Z with respect to multiplication, because 1 is inverse of itself, because 1 times 1 will give the 1. 1 is the identity element here with respect to multiplication, and minus 1 is also self inverse, because minus 1 times minus 1 will give us the identity element here. Whereas 2 is not invertible in Z dot, because only integer, I mean there is no integer if we multiply with 2 will get 1, this identity element, right? Because only element is 1 by 2, but that doesn't belong to an integer set. And therefore these are the only, I mean no integer apart from these two having that inverse, and therefore these are the only invertible element in this monoid Z dot. Well, when this inverse exists of an element, this actually exists uniquely. So how can you see this? Suppose, and this holds in a monoid, because associativity criteria we need to have, otherwise can't prove it. So let G composition be a monoid, and let's say B and C are two inverses of an element A in G. Then by the definition of inverse, A compose B equals B compose A is the identity. Likewise, A compose C equals C compose A is identity. Now we can apply this associative property so as to obtain B compose A compose C is same as just changing the position of parenthesis. So B compose A compose C. Now just putting this value, this is equals to identity and this is identity, so we'll have B equals C. And therefore if inverse exists of an element in a monoid, then it exists uniquely, and that leads us to denote, we have to follow this notation. If A is invertible element in a monoid, then its inverse is denoted by A to the power minus 1. Okay. Alright, now we'll see another interesting thing. In a monoid, if an element A is left invertible as well as right invertible, then A is invertible. Okay, let's see the proof. Let B and C respectively are the left and right inverses of the element A, which amounts to say B compose A is the identity element and A compose C is the identity element, because B is the left inverse of A and C is the right inverse of A. Now, since it is a monoid, we have the associative property. So, if we apply this associative property, keeping A in the middle and around A, B and C are there in the correct order, then we will have B compose A compose C is equals to this B compose A compose C, and then just putting A compose C is identity, and here this is equals to identity, we will have B equals to C, and therefore A compose B equals, B and C are equal, so A compose B equals B compose A equals to identity, which amounts to say B is the inverse of A, that is B is A inverse. Well, before I conclude today's session, we'll see a solution of a problem based on this idea. So let's do this now. Well, here comes the problem. Let M be a finite monoid. An element A belongs to M is right invertible, then show that A is invertible. Let us see how can we solve this problem. So, given that A belongs to M is right invertible, which means there exists an element B in M such that A B equals to identity, which means A compose B equals identity. Alright, now we construct this function f m to m given by fx equals xa. Now we want to show that f is injective. So fx equals fy will give us xa equals ya by the definition, and then we compose b on the right of both so as to obtain this equals this. Now by using associative property we can change the position of parenthesis so as to obtain xab equals yab, and we are given that f equals identity, so x equals y, and that means x equals y. So which means fx equals fy implies x equals y, that's injectivity of the function f. Now see here, given that M is a finite set, so injectivity is equivalent to surjectivity. And for a proof, you can check a link in the I button where I already shown this result. Anyways, so F is surjective, which amounts to say every element here has a pre-image. That means in particular identity element here also has a pre-image. Let's denote it by C. So there exists C in M such that F of C is identity. So by the defining property of F, this is C times A is identity. So what it means? That means A also has left inverse, or A is left invertible. Now from the previous observation, you can conclude that A has right inverse, A is right invertible as well as left invertible, and therefore A is invertible. And always we can prove this by using this associativity, just like before, that taking A in the middle and B and C in the correct order around A, will have this, and that will follow that A is invertible. Okay, so thank you for watching this video, and see you again next video. Thank you once again.